Thanks for staying for the very last talk of the day. We hope to make it somewhat interesting. So first, I want to show you some images. This one. And what do they all have in common? All of them have sparse and high albedo geometry. So the goal of this paper is to render scenes such as these ones with sparse and very high throughput surfaces, such as this asteroids field, which are very challenging for most methods that rely on directional sampling. But why is sparse geometry so challenging? So here you can see the sparse geometry in the gray surfaces and light in yellow. And we are trying to compute the outgoing radiance at a given point x, which is the classical rendering equation. And for this, we need to compute the incident radiance, which is plotted in orange here, which, as you can see here, because direct light is occluded, most of it comes from one bounce in the sparse geometry. So if we were to sample directions in the hemisphere of the shading point, we get very few hits, as we just saw in the previous presentation. And therefore, we have a huge variance since these very many samples in gray, shown in gray here, do not contribute anything. In the same way, if we were to do light tracing, we would also get very few hits. So this doesn't solve the problem. And this problem, you can see, is very, very similar to some other cases in rendering, such as scenes with very many small lights, where the solid angle sampling is also not ideal. And randomly sampling directions would be very bad as well. And this is because the incident light field at the point is very high frequency, angularly. And this is solved by doing next event estimation, which directly samples the emitters, of course. So we propose to do something very similar for our sparse surfaces. So to directly sample the high contribution connections in these reflectors, in the geometry of the scene. But the problem is, what is the best additional vertex to sample? Is it this one? Maybe this one? So to devise our solution, we draw inspiration from mainly three categories of works. So first there is extended next event estimation works, such as the ones by Hanika et al. Or many-fold-based next event estimation, which inspired us with this idea of importance sampling and additional vertex. And continuing with the many lights analogy, we were also inspired by hierarchical sampling methods, such as the one by Conti and Kula, because we needed a very scalable way to sample a great number of small surfaces. But we were still missing some heuristics for this top-down traversal of our hierarchical structure. And for that, we drew inspiration from aggregate appearance works, such as the recent one by Zhou et al., which allow to consider the total contribution of several surfaces in a statistical way. So we use this to expand the information in each node of the scene's VBH with some useful statistics that describe its aggregate appearance. So going back, we formalize our problem. We are trying to compute the integral of this light that reaches the point, which is the integral of the contribution of every single surface connecting the emitter to the shading point axis. So our goal is to importance sample this integral by picking a high contribution xn, as we said. So more specifically, this would be with a probability proportional to its contribution, which, however, has the typical problem of containing the same integral that we are trying to compute. And moreover, it is impossible to pre-compute, since this PDF, as you can see, depends on both the shading point and the emitter, which will vary across every pixel and emitter. So we will now detail our solution, talking about the three main steps of the method. First, there is the hierarchical sampling, top-down, of our structure. Then our practical node importance weight to do this selection, top-down selection. And finally, we will discuss the aggregation of statistics bottom-up. So first, let's focus on hierarchical sampling. So let's first decompose the PDF. To sample this point xn on the geometry, we need to decompose it as the product of two terms. The first one is the discrete choice of sampling a primitive, which are colored here with the purple things. The discrete choice of sampling one primitive and then sampling the xn point in the primitive P. And in this work, we assume that the scene geometry is made of primitives small enough or tessellated enough so that the points inside a single primitive have a similar contribution. So that sampling the primitive P is the most important part. But this is still quite challenging because it would require computing the whole tabulated PDF for each of the primitives in the scene. It is, again, impractical or impossible because it depends on XS and XE. And to solve all of this, the first thing that we do is use this hierarchical approach, which also drives down the asymptotic cost from O(n) in the number of primitives to a logarithmic one. So to do this hierarchical sampling, to compute this discrete PDF to pick one primitive, we start from the very top of our hierarchical structure of the scene. So the top node in purple here contains the whole scene. And we evaluate the weight of its two children in blue, which would be ideally the whole contribution of all of the geometry in that node, in those nodes. So in this case, as you can see, the left child is more important, so it will likely be picked. We do the same for the two children, which are in green, and continue down, in this case, picking the right child, until we finally reach a leaf node. And then we can finally sample the point xn inside of that primitive. So now Jorge will continue with some maths.
So Nestor has told you that we need a node importance weight to guide this traversal. But what is this node importance weight for each node? So ideally, the importance weight of this node is proportional to the total contribution of the geometry contained in this node. However, as we have said, this will require to solve this integral and or pre-compute it, which cannot be done. So our goal is to create or to obtain a good enough approximation of this importance weight, which is quickly to evaluate. And for that, we ask ourselves if there's a way to estimate the aggregated contribution of all this sparse geometry of a node in a single fast evaluation. The solution that we find is to change to a statistical formulation, which allows us to treat all the geometry of the scene as a continuous cloud of geometry, which can be described with aggregated statistics. Basically, what we are doing is breaking this node importance weight into three main terms: the spatial distribution, which tells us where the geometry is scattered in space in the scene. We have some directional distribution, which tells us the orientation of the normals of this geometry. And we also have some material distribution, which tells us the reflective properties of this sparse geometry. Then we are going to now see how we can leverage this statistical formulation to compute a practical node importance weight, which can be fastly evaluated. For that, what we first do is we decorrelate the spatial and normal distributions. And this allows us also to reorder them. So we split the spatial and the normal and material distributions. Then we just group them for clarity in this derivation. And what we saw is that the reflective properties they have very different behaviors. So what we choose to do is to split them into diffuse and specular components to approximate better these material distributions. Just to get an idea of how this diffuse and specular aggregated appearance can be evaluated, The diffuse appearance basically depend on the mean albedo and the normal distribution of this sparse geometry, while we are able to represent the specular material, the specular aggregated behavior, as a roughened microfacet model. And what we do here is, in reality, we are convolving the microfacet from the specular BSDF with the macronormals, which are given by the orientation of this geometry, of these normals of the geometry. And this is possible because we represent both as a BMF distributions. With respect to how do we evaluate this integral, what we do is we choose to compute it by evaluating the terms of this integral at a sparse point along all this spatial distribution of our representation, which we choose to be a 3D Gaussian. So now that we have seen that we will compute our node importance weight, we are going to show which aggregated statistics are needed to compute it. So yeah, as we've seen, the approximation of this node depends on some aggregated statistics, but we want this node importance weight to be evaluated quickly. So for that, we would like them to be pre-computed so that we don't have to pre-compute it at every time that we are evaluating this expression. So how do we compute them? What we do is we start from the leaf nodes, which contain simple primitives, where we are able to just perform an area-weighted fit of these primitives in basically the spatial we get as a Gaussian, as I've said, normals a BMF, and from the material, what we do is we take the mean of some of these properties, so mean albedo, mean roughness, mean specularity. Once that we know like these statistics from the children, the question is how we do the aggregated statistics for the parents. And what we have chosen to do is leverage the statistics that we already know. We leverage the statistics from the children nodes, and we just perform an area-weighted sum of these children node statistics. And this is possible, in fact, because what we are doing is internally we are not representing these these statistics as we have presented it here, but rather we represent them as some raw additive statistics that we develop further in the paper. So now that we have finished the methodology of our method, we are going to present some results. So first, we are going to show the results on this indirect illumination scene, where we have a lot of asteroids. We have some camera and some distant emitter, and the question that we want to answer is what's the radiance, what's the light that is arriving to some of the faces of these meteorites. However, the problem of this is that the majority of this illumination comes from the other asteroids. So it's not as easy as doing next-end estimation. In this case, what we do is we leverage our technique to compute the outgoing radiance of this shading point XS by by sampling these 3 vertices paths that go from the shading point to the emitter through an additional vertex sampled directly on the geometry of the asteroids. We compare our technique against path tracing, bidirectional path tracing, and practical path guiding. All of them are techniques which leverage directional sampling, and in contrast, our technique which leverage this additional vertex directly sampled on the geometry, what allows us to do is converge faster at the same number of samples per pixel. Our technique remains competitive at equal time comparisons, since the additional cost of this the sampling this additional vertex is amortized by the quality of these samples. So here we show a plot of that our technique remains competitive along all these like effective render time, and even though practical path guiding at the end becomes closer to our method, it requires a higher memory consumption. Even more, our technique is applicable to direct lighting. In this case, what we have is a lighthouse with a lot of very small discrete media, which you can think of snow. And again, we have a camera, and we have 2 spotlight emitters as the light of this lighthouse. In this case, what we do is the shading point is directly positioned on the camera, And what we have to try to do is to sample this additional vertex on this sub-pixel size discrete media that we have presented before. And because these particles are extremely small, these particles are sub-pixel size, they create an extreme sparsity problem for path tracing. And to see this how this reflects, just compare this render which we perform using path tracing in comparison with our method, which shows how path tracing misses a lot of this sub-pixel size media that path tracing is not able to intersect. This is even more visible when we use like distributed effects, like depth of field. Here, path tracing has required like 36 minutes to get this result, while our method is able to get this converged render with in just 100 seconds. Finally, the applicability of our method. Greatly reduces the variance in target scenes, but it incurs some cost per sample, and this overhead is not worth it when directional sampling is already good, such as this cornel box example. And some future work, our hierarchical sampling, we could try to reduce the overhead cost by using techniques like tree sampling or like reusing some samples. The not important weight, we could approximate better, since right now we don't take into account visibility. And for aggregated appearance, we can explore alternative representations like EGSR or Gaussian process implicit surfaces, as has been shown before. So thank you for listening.
Thank you very much. Any questions?
Very nice work. Thank you for the presentation. I was wondering, if you have this light hierarchy style thing, the usual problem is that you take a wrong turn at the early decisions, like when the tree is still coarse, and the Sony light hierarchy took explicit measure to make up for that. By the time you notice if the estimate is good enough, then the sample is essentially void. Do you do something similar?
Sorry?
Do you do something similar, like recover from a wrong turn you take when you descend down the hierarchy?
Yeah, I heard. So you mean, like stopping the search once you know that you are not going to get a good sample, for example?
Yeah, more the other way around.
The other way around. Okay.
The usual measures are either start 5 random samples in the beginning and just take the best survivor or something, or you subdivide like 16 times and start not from the root because the coarse estimate is so bad.
Yeah, no, we don't do that, the short answer, and it's definitely one of the main avenues for future work for sure, like doing, for example, splitting also, or Richter, as we mentioned briefly, like the last work by Conti in 2024, where they mix this light hierarchy with some resampling of the final samples. Some of that is definitely worth exploring, but we haven't done that yet.
Okay, cool, thank you.
How far have you looked into the possibilities of this technique in the context of sampling light transport in hair?
You mean in air?
In hair.
Oh, in hair. We did not explore that, but definitely if our technique it's targeting like sparse scenes, so I think it will be more effective if it's like a close-up of the hair or something like this. But if we are taking more of a like aggregated appearance of hair from far, which can be thought of like a continuous like surface, in that case, I don't think our technique will be like the best one. So I think it will be depending on the scene and which part of the scene we are like looking at.
Okay.
Do you take into account the BSDF at XS or the directional distribution at the emitter as well?
Yeah, in this practical node importance weight, basically this directional term, which takes into account is all of them. So the directionality of the meter, that's more easy, or that's easier, since we just evaluate this node importance weight at different points in this spatial distribution, and also for the BSDF at this intermediate vertex. You mean at the intermediate vertex or at the shading point?
At the scattering vertex, XS.
And at the shading point is similar to the emitter. We just evaluate this BSDF depending on where we have chosen this intermediate vertex. So you have like a outgoing direction from this intermediate, from this shading point.
Okay, thank you. One more?
Do you think it could work if you have transparency? For instance, if you have like a dense tree with foliage and stuff like that?
Yeah, that would be interesting for sure. But I think we would have to add another term. We have here the diffuse term, the specular term. We would need an additional one with the transparency, which we don't have. But yeah, I think it should not be too hard to accommodate that.
And,
nice.
Yeah, and also maybe we should change the directional distributions, since now the normals can be like back-facing, let's say.
You will need
exactly.
like two lobes, basically.
Exactly.
Yeah. Okay.
So it might be like 2 node importance weight, one for each.
Okay, thank you.
Thank you. Let's thank all the speakers of the last session, I guess.